Images of space begin as black and white. Here's how they get their color. The stunning images of space that capture our imagination undergo a fascinating transformation from grayscale to vibrant hues. Take a moment to examine the image above. What do you notice? Do you recognize anything familiar? It's clear that this is a space photograph, likely captured by a telescope. This particular image is one of NASA's most celebrated space photos, even if it's not one you've encountered before. How can I tell? It's simple, it's in black and white. You may be surprised to learn that nearly all space photographs begin their journey in this monochromatic state. In fact, most telescopes, including the renowned Hubble telescope, primarily capture images in black and white. Now, shift your gaze to the colored version of the same image. While it resembles the previous one, this vibrant depiction is far more recognizable. Known as the Pillars of Creation, this breathtaking photograph of the Eagle Nebula, located 6,500 light-years away, showcases the remarkable process of adding color to space imagery. So, what exactly is this process, and what does it achieve beyond simply enhancing the colors of space photos? Let's explore further. How does this process work? Before delving into the coloring of space images, it's essential to grasp the nature of light in the universe and our perception of it. The spectrum of light encompasses all frequencies known to us, from radio waves to gamma rays. However, we can only perceive a small segment of this spectrum, referred to as visible light, which is highlighted in the diagram above. This visible light ranges from red at the lower end to violet at the upper end. Our ability to see this light is thanks to specialized cells called cones located at the back of our eyes, which interpret the colors of objects based on the light they reflect. Our retinas contain 3 types of color-sensitive cones, each attuned to different light wavelengths. These cones respond to long, medium, and short wavelengths, which correspond to the primary colors of light: red, green, and blue. These primary colors form the foundation for all the colors we perceive. You may be familiar with the RGB model, where varying combinations of red, green, and blue light are blended to produce a wide array of colors. This model is widely utilized in electronic displays and is vital for understanding how space images transition from their original black and white format to vibrant colors. With a solid understanding of light established, let's explore the process in detail. The space images you often encounter are predominantly captured by the Hubble Space Telescope, so we'll use it as our example. Initially, the telescope must be accurately focused, as its subjects are typically located at great distances. Proper adjustments are crucial for the telescope to capture clear and detailed images. The camera then begins capturing the image. The light observed by the telescope is divided into long, medium, or short wavelengths, resulting in 3 distinct images that correspond to each wavelength range. However, this procedure is time-consuming, with each frame requiring a significant duration to capture. Some estimates suggest around 1,000 seconds. Moreover, as Hubble orbits the Earth at a speed of 17,000 miles per hour, it often needs to complete several orbits to gather all the necessary frames. Once the images for each wavelength range are captured, they are assigned colors based on their position in the color spectrum, typically red, green, or blue, following the RGB model. This technique is known as broadband filtering, where the incoming light is sorted into broad categories of long, medium, and short wavelengths. Subsequently, the various frames that capture different light wavelengths are merged into a single image using software like Photoshop. After some enhancements, the final photograph is ready, resulting in stunning visuals like the one shown above. What other applications does this process have? Spitzer Spies supernova remnant HBH3. While witnessing space in vibrant colors is a breathtaking experience, this process also serves important scientific purposes. For instance, researchers can utilize both broadband and narrowband filtering techniques to identify gases and their presence in the cosmos. When studying the remnants of a supernova, scientists can determine which gases were present or released during the explosion. Since different gases absorb various wavelengths of light, the colors assigned during the imaging process are crucial. Understanding how common gases manifest on the spectrum can provide astronomers with insights into the distribution of gases throughout the universe, potentially offering clues about extraterrestrial life or other galaxies and systems. What lies ahead for us? The universe is an immense expanse filled with wonders that humanity may never fully comprehend or experience. We've only scratched the surface, having explored merely 5% of our planet's oceans, and our journey into space is just beginning. Yet, our determination to push forward remains unwavering. While our current understanding of the cosmos is limited to theoretical interpretations, it won't be long before we can capture vivid images of space, bringing it to life in stunning detail. In the interim, this broadband filtering technique holds immense potential for humanity, aiding us in discovering habitable planets and delving deeper into our vast galaxy. Every day, we are pushing limits, fostering innovation, and overcoming obstacles. The quest for innovation is relentless, driven by an enduring desire to tackle the challenges facing our world. I eagerly anticipate witnessing this progress unfold in the years to come.